All of trigonometry is based on angles. Okay, so where previously, when you learned like the basics of algebra and you didn't even know you were learning algebra back in like 6th and 7th grade, they taught you about the x-axis and the y-axis and how x's go side to side, positive and negative, y's go up and down and all that good stuff. The x and y-axis, it's still here. However, we've kind of overlaid that with a circular kind of motion here. So angles, as we know them, work in a circular pattern. So we start talking about angles and their positions by saying, okay, an angle is in standard position if a couple things are true. One is the vertex of the angle is at the origin. That's where the two sides of your angle come together. That's your vertex, okay? And then we say, or label this as its initial side here. We say the initial side is on the positive x-axis. So we still have an x and a y-axis here, but we're going to be doing a whole lot of talking about circular movement here rather than left, right, up, and down. So while you can't really like see this in a drawing, what you have to picture is almost like old school clock hands where they sweep around. Okay, so if you think about an angle, the measurement of an angle is actually this circular rotation that you are doing. So that particular angle that is drawn there can actually be measured in two different ways. Typically, we go counterclockwise to show a positive angle. So if I rotated that initial side and went in a counterclockwise direction, that would be a positive angle, and I could say maybe that's about 135 degrees. I'm just kind of guessing, okay? Now, we could also measure that angle going in a clockwise direction. And if we did show that in a clockwise direction, it would be a completely different angle, right? Because that's a different amount of rotation going backwards than it is forwards, right? We should remember from geometry that from here to here would be how many degrees? 90. So this is 90. This is another 90. So we're at 180. And if I said maybe that's like 45-ish, I don't know, I'm just taking a shot at that. It's not really a specific picture. I could say that this is about negative 225 degrees. Right now, we are just estimating, right? I'm just saying about how much forwards or backwards. So showing me which way your angles are rotating is going to matter for right now, especially. Showing me whether it's rotating forwards or rotating backwards, okay? So counterclockwise is positive. Clockwise is negative, okay? And some of what we're going to practice today is literally how do we draw angles and what do they look like, okay? I know that sounds very basic, but we need to get into that kind of theory here. We typically will see Greek letters like theta, beta, alpha. If you don't know those, write them down over here for you. This one is a common one, theta. The capital B one is beta. And the fish-looking one is alpha. The very end of today, we're going to use alpha for a very specific type of angle. So you're going to see that one there. Theta will be common for us a lot. Okay? So you're going to see those or capital letters representing angles. And now the other major thing we're going to talk about today is how rotation can be measured. All of us are comfortable from geometry and like science classes and stuff like that with degrees. Like if I told you what does 90 degrees look like, you could tell me. Here's this 90-degree angle makes a perpendicular line, and we know that. What does 180 degrees look like? We know that. We could estimate what 120 degrees looks like. But there is a second way of measuring angles, and that is called radians, okay? And now just so you kind of know the theory behind what we're going to be doing here, in this unit, we're going to spend time talking about both degrees and radians, kind of interchangeably. We'll do some this one, some of that one. We'll just work with both. As we progress through this semester, we are slowly going to lose degrees and pick up all radians, okay? And this is because calculus, which is most of us, more of us will be, that's our next step. Calculus is all radians. So by that point, I need you to be comfortable with them. So we'll start with what you're comfortable with now and build into that is kind of the idea, okay? So a radian measure comes from, and you don't really have to know this, but I'll tell you anyway because it helps you. We know in our minds that 360 degrees would be like the whole way around the circle, right? If I did one full circle around 360 degrees. Radian measures comes from that idea. The other way to go the whole way around the circle is to measure the circumference, which is 2 pi r is your circumference, okay? So using the idea of circumference, we know then that 360 degrees is the same as what we would call 2 pi radians. Okay, those are equivalent. If 360 degrees is the same as 2 pi radians, a simpler version of that would be that 180 degrees would be equal to what, do you think? If 360 is equal to 2 pi, what's 180 equal to? Pi, half of it, okay? And we're going to use this at the beginning to convert between degrees and radians. Because while we can picture a degree in our head and we can think about what does 90 degrees look like, we do not picture radians in our head at the beginning. And part of my job in this unit is to get you to the place that you can, okay? So I'll go back. We're going to practice converting. In order to convert, we're going to use a simple proportion. Because we just said 360 degrees is the same as 2 pi and 180 degrees is the same as 1 pi, we're going to use the proportion degrees over 180 equals radians over pi. So to convert anything between degrees to radians or radians to degrees, we're going to use the same formula. So if I'm asked to convert negative 225 degrees to radians, all I have to do is plug that number in for degrees and solve for radians, which will be my x, essentially. So I'm going to say, I'm given negative 225 degrees, it's always over 180, equals, I'm trying to convert 2 radians, so radians is my x over pi. Now we all know how to do proportions, right? What's the best way to solve these? Yeah, it's like the butterfly method, right? Now, a lot of us know, though, instead of having to like multiply, and then divide, we know it's like multiplying these two and then dividing by this one, yes? Yes. Okay. So real quick then, I'm not actually going to take 225 and multiply it by pi, right? We know pi is like 3.1415, blah, 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 blah. We don't want the decimal. So what you're going to see in trig is there's going to be a lot of answers with pi's in them. Because pi itself, the symbol, is more accurate than the decimal. We don't like the decimal. So if I multiply that and divide, it's like I'm taking negative 225 and sitting it next to pi, because it's like I'm multiplying by the 1 there, right? And I'm dividing by 180. Now I want to always simplify this. So what can I do in order to simplify this? I mean, if you don't know exactly what both like the greatest common factor is, what can we start dividing by? 5. We at least know it divides by 5, right? So if I went through that, 225 divided by 5 would give me negative 4 goes into 20, and then 25 is 45. All right, so then 180 divided by 5 is going to give me what?
26.
So 5 goes into 18 3 times, with 3 left over, 36. So if I divide by each of them by 5, I get here. Now, does this keep dividing? Do I stop here? No? What does 45 and 36 both divide by? 3, 9. Let's go with 9 because it's the biggest one, right? So 45 divided by 9 is 5 pi over 4. And that is fully reduced. So you would say, as a radian, like we're used to degrees, again, we see the degree symbol there, right? This is negative 5 pi over 4. Like that's verbally how you would say that. You do not have to label that as a radian, okay? It is understood if there's a pi in it that it is a radian, okay? So that's kind of like a label. It's not, but it is. Also, just generically in trig, if something is a degree, it has to have a degree sign, yes? If it does not have a degree sign, it's automatically assumed to be a radian, okay? So just understand that going forward, okay? All right, so take a minute then, use the same proportion and try number 4. This has a little bit smaller numbers for us to work on for our first day back here. you'll stop feeling like you're actually cross multiplying because it's like, okay, so it's really the 50 over 180 and stick the pi next to it, right? So that gives me, when I reduce, this one's easier, right? Because we know they both divide by 10. 5 pi over 18. Yes? Now, when we go the opposite way, notice when you are given these in 5 and 6, they don't say, like, convert this radian to a degree. First off, it just says convert this, negative pi over 3, to degrees. So obviously it's not a degree because you're converting it to degrees. Secondly, if it's got a pi in it, we assume it's a radian. Okay, so this time my x is degrees, and I'm given my radian. Now this appears as if it's initially going to be very ugly. However, one small detail about fractions that will help us. What do we remember about fractions? If something's the same top and bottom, what are we allowed to do with it? Cancel. Okay, so there's a pi on top, and there's a pi on bottom. They go away, but there's still a number there. What is the number next to each one of them? This is like a negative 1. And down here, it's like a positive 1, right? Because if there's no number in front of something, it's an assumed 1. So every time you're given a radian, the pi's are going to cancel because you don't want pi in your answer for degrees. That's only for radians. So when I convert, this time I actually do have to cross multiply more, okay? So I'm multiplying this way now. What is negative 1/3 times 180? Negative 60. Now, do I really have to divide by 1? No, right? Anytime you do this way, like it's never really going to matter with that on the bottom because the pi's are always going to cancel. And you're just going to be left with the degrees. So it's really just multiply that way. So negative 60 degrees is the same as negative pi over 3. A negative degree should be a negative radian and vice versa. Like the positives and positives and negatives and negatives. Because in this, the negatives and positives just mean which way you're rotating. Remember the first page we said a positive means you're rotating counterclockwise. A negative means you're rotating clockwise. Okay? So take number 6 and try the same thing. And then we'll start practicing drawing angles. Now, because I made a big stink about if it's not labeled with a degree sign, it's assumed to be a radian. Like your degree sign needs to be there. Yeah? Okay, just make sure of that. All right, so the next thing we're going to do here is just start practicing drawing angles. Again, we're going to feel way more comfortable with the idea of doing degrees versus radians. It's going to be something that doesn't come as easily to us, okay? So, first thing, we have these angles, specific angles called quadrantal angles. Now, I don't need you to know that name. Quadrantal angles are going to just be kind of like home base angles for us. They're the ones that fall on all the axes as we go around, the x and the y axes. So what that's going to look like, and my drawing skills always leave a little bit to be desired, but that's okay. I've got an xy axis here, okay? And I'm just going to walk through the different quadrantal angles in first degrees because they will make sense to us, and then we'll switch to radians to like align which ones go with which. Okay, so first off, 0 degrees, okay? We said the first angle, or for an angle to be in standard position, it always starts on the positive x-axis. So if I was to draw a 0 degree angle, it would just look like a line because it's rotated 0 degrees, right? So 0 degrees would be right there. The second quadrantal angle will be a 90 degree angle because it will start on the x-axis and finish on the y-axis. So when I draw that one, I'm going to kind of overlap mine. You can do how you want to do, but I'll kind of do mine in different colors so you can see here. I'm going to show my initial side on the positive x-axis. I'm going to show what we call the terminal side where it finishes on the positive y-axis, and I'm going to show which way I am rotating, 90 degrees. So any guesses what our next quadrantal angle would be? 180. 180. You can pick it up fast, right? So 180 would start on the positive x-axis, end on the negative x-axis, and I would show my rotation from here to here. Positive 180 degrees. So if we're continuing our pattern, what would be my next quadrantal angle? 270. They all start in the same spot, if we're not picking that up yet. Here is the initial side. Here is terminal side. we would show our rotation the whole way around 270. And then we have one final one. What's our final one? 360. And our 360 one would look a whole lot like 0 degrees except for one difference. It would be a big rotation around. There is my 360 degrees. And so like I said, with degrees, we're really familiar with those. Like 90, 180, 270, 360. Like this feels good to us. Each of these has a corresponding radian. Okay? And those at the beginning, it's just going to be something that will end up being in your head because you'll know which ones go with them. So just understand that. It'll feel like, I don't know, it'll just feel weird for a little bit. And then it'll get more comfortable, I promise. We already talked about a few of them when we talked about converting between them. In fact, we said 360. Anyone remember what 360 was the same as? 2 pi. And we also then, for our conversion, said what 180 was the same as. 180 was the same as pi. Now, the reason I bring that up is because radians follow patterns just like degrees do. Degrees go up by 90 every quadrant, right? It goes 0, 90, 180, 270, 360. Well, you can already kind of see a pattern in the pies, right? A full rotation is 2 pies. A half rotation is 1 pi. What do you think a quarter rotation would be? Half a pi. So 90 degrees is what we're going to call the same as pi over 2. Half a pi. Which means if it's going then in the patterns there, it's going 0, half a pi, 1 full pi. What do you think's next down at 270? 1.5, which we would call what? 3 halves. 3 pi over 2. And so really, this is a very messy drawing, but if you want to kind of make yourself a cleaner version, I always do this to myself, we're going to kind of use these as reference points. So we're going to know this is 0 degrees, which is 0 radians. We're going to know this is 90 degrees, which is pi over 2 radians. This is pi, which is 180. This is 270, which is 3 pi over 2. And this is 2 pi, which is 360, okay? So these are going to be reference points for us for when we start drawing angles then on the next page. So when I ask you to draw an angle of 120 degrees, the reason we know how to do that, whether you think about it this way or not, is because you know what 90 looks like, and you know what 180 looks like, and you just estimate somewhere in between those for 120, right? And that's what we're going to do with radians too. So for radians, it's going to be good for you to have kind of like what the quadrants are so you know where to place the other ones in between. Okay, and that's how we're going to handle that here on the next page. We're going to start with just drawing regular angles with degrees, and then we're going to start drawing some angles with radians and start getting comfortable with that. So if I asked you to sketch a 120-degree angle, like I just said on the previous page, you would think to yourself, well, I know this is 90, and I know this is 180, so I know 120 falls between them, right? I'm not asking you to like pull out a protractor and draw an angle like that. I'm asking you to just sketch it. So would you say, should 120 be closer to 90 or closer to 180? To 90, yeah, because it's only 30 degrees from 90, where it's 60 degrees away from 180, right? So if I'm sketching this, I'm going to draw, and just some good practice to draw here, my initial side. I'm going to pick a place between 90 and 180, but I am going to make it closer to 90 because I'm smart enough to do that. Okay, I don't just draw it right down the middle because I'm lazy. I say it's okay, it's closer here. And I'm going to say, okay, from here to here is about 120 degrees. Yes? So right now when we're drawing angles, we're going to be very specific about drawing our arcs to show which way they're going, to show they're positive or negative. Because in just a second here, we're going to draw a negative angle, right? And negative angles mean we go backwards instead of forwards, okay? So this is where, for some of us, we actually have to think about, okay, forwards and then backwards, and then what does that look like? So for negative 45 degrees, and it will be different for each one of you how this works in your brain. So there's always things that, like, when I teach this, I say, like, this is how this works in my brain. It might not work that way in your brain, and I get that. But when I do a 45-degree angle, but it's negative, I think to myself, okay, the amount of rotation going forwards is about, well, it's exactly half of a quadrant, right? That would be what it looks like going forwards. So then when I go negative 45, it doesn't mean rotate backwards to get to where 45 was. It means rotate that same amount backwards. So instead of going half a quadrant forward, I'm going to go half a quadrant backwards. Because some people, every year, I have it happen, that you think you're rotating backwards till you hit where 45 was, like the whole way backwards. Don't do that. Same amount as you would do forwards, but backwards. Yes? All right, so I'm going to give you 2 to practice that real quick. I would like you to sketch 240 degrees as well as negative 315 degrees. All right, so do we feel confident jumping or doing degrees before we jump into radians?
Yes, ma'am.
Yes. All right. Okay, so radians. Here's going to be the real reason some of us decide we detest radians. And it's because there's fractions. Like, we just don't like fractions still. We've been doing them since 4th grade, and it's still just our nemesis, okay? So, in order to do radians, you really need to know those quadrantal ones that we started with, because those are going to be kind of our guideposts. So, before I ever get started, now, by the end of your homework on the first day, I don't want you to have to label these every time, but at the beginning, it's perfectly fine to remind yourself this was 0 radians, this was pi over 2, this was pi, this was 3 pi over 2, and this was 2 pi. Because right now, these are going to be kind of like helping us organize our thoughts as to where these are. Now, the pi's throw us off, but when everything has a pi in it, couldn't I just think about the numbers and ignore the pi's? And that's exactly what we're going to do. So when you see pi over 2, I want you to think about that more like 1/2 or 0.5. Because everything has a pi in it, so the pi doesn't really matter for that when I'm graphing radians. And then pi is really just like 1. 3 pi over 2 is like 1.5. And 2 pi is just like 2. Yes? All right, so when I am graphing, or asked to graph, 5 pi over 4. So if I'm asked to graph 5 pi over 4, I draw my initial side. Same place I always do. 5 over 4. Where does that fit in terms of like these numbers that I've written around here? 5/4 is about 1.25. So where does that fit? In the 3rd quadrant, and directly between 1 and 1.5, right? And so that's exactly what I'm doing. Anytime I think of these, I think about the fraction and where it would fit in between the other fractions. And if you need to think about it as a decimal, then do it, okay? So that means this goes halfway into this quadrant, and I show it going around in a positive rotation, and that is my 5 pi over 4, okay? Negatives work the same way. You just have to think of the amount of rotation forwards and backwards. Now, when I'm asked to do 3 pi over 2 in a negative direction, I already know where positive 3 pi over 2 is, don't I? Yeah, that's down here. Okay, so when I do a negative 3 pi over 2 rotation, and I'm not going to ask you to draw this right now, but this is what I'm thinking in my head again. I'm thinking to myself, okay, so to get to positive 3 pi over 2, I have to rotate the whole way through 3 quadrants forwards, right? So if I need to do that whole same amount of rotation backwards, I have to go through 3 full quadrants going backwards. 1, 2, 3. So negative 3 pi over 2 would end up back up here. So think for negatives the same amount of rotation forwards as you go backwards. Now, like I said, the radians will always feel a little bit more uncomfortable than the degrees. So we're going to practice at least two more of those. Okay? All right, so in your little practice space, let us practice with graphing. Let's do 2 pi over 3 and negative 3 pi over 4. See how we do with those. My practice one's here. So I'm still thinking in terms of my quadrants. I've got 0 pi, 0.5 pi, 1 pi, 1.5 pi, 2 pi, and so on. Now, I would probably actually write the pi's, but 2/3. 2/3 is about what? 0.6 repeating, yeah?
Yeah.
So where's that going to fall? What quadrant?
In between 0.5 and 1.
It's in between 0.5 and 1, and probably closer to which one? Probably closer to 0.5, yeah? So that is going to be about there. And that's going to be my 2 pi over 3. How did we do with that one? Good? All right, now, negative 3/4. Okay, again, as a decimal, 3/4 is the same as 0.75. So I tend to think about these like, where would I be if I went forwards? Do that same amount backwards. So 0.75 for me, forwards would be there, yes? But if I go backwards, where am I going to be? What quadrant? Third. I'm going to be right in the middle here. 3/4 backwards. And again, there will be several questions like this on your homework so that you get in the practice of being able to graph these. I know those are a little bit at the beginning. Okay? All right. 2 more major terms we have to talk about for today, and then I will be done. I have till 11:50. Oh, I'm doing good. Okay. Coterminal angles. So part of the nature of angles is that they keep going. And by that, I mean you can rotate around and around and around and around and just keep going. So coterminal angles are angles that have the same terminal side. And while that doesn't necessarily make sense to you right now, it will in just a second. So there are 3 pictures here. All 3 of these pictures have an initial side on the positive x-axis and a terminal side that's right about there, that same location. This one has the same initial terminal side. This one has the same initial and terminal side. Well, how can that happen? Well, because you can get to those angles different ways. We've already talked about 2 of those ways. One of them is a positive rotation, which you're seeing here. A positive 30-degree rotation lands me right there in the first quadrant. Well, a negative rotation, like you see over here, also lands me in that same spot. It just takes more degrees to get there in a backwards direction. But those still have the same initial and terminal side, so they are called coterminal angles. Well, that's not the only 2 that work that way, because I could rotate even more. So the only difference that you're seeing in this third picture, how are we getting to 390 degrees? Yeah, you're just keeping on going. You did a whole circle and then another 30 degrees. What's stopping me from going around another time? Nothing. Okay? Yeah, that's the actual answer. Nothing's stopping me. I can keep going and going and going and going. So in order to find angles that have the same terminal side, you can either add or subtract a full rotation. In terms of degrees, that's how many degrees? What's a full rotation? 360. In terms of radians, what is it?
2 pi.
2 pi. Good. So if I was asked to determine 2 angles, and this won't make sense to you now, but next class, when we start actually finding trig values, 500 isn't going to make a whole lot of sense to us, because when we find trig values, we're going to do it all within 360 degrees. So if you're ever asked to find something about 500 degrees or even how to sketch it, I wouldn't sketch 500 degrees. I wouldn't think like, oh, let's go the whole way around this and do this again. I would think to myself, well, I can back that up into like, where would it be 0 to 360 by just subtracting 360 degrees. If I just subtract 360 degrees from 500, what do I get?
140.
140. And so I know where 140 is in my little quadrant system. It would be so much easier for me to graph 140 and know where that is rather than thinking, okay, I have to go the whole way around and then another 140 degrees and this is where it would be. So being able to add and subtract is going to help you a whole lot of other ways. But again, you could find one backwards by subtracting 360. You could find a larger one by adding 360. Easy enough. 860 degrees would look the same. I could find a negative angle by continuing to subtract 360 from 140. It's not real hard to do this. It's just weird at the beginning. So the same thing, if I didn't want to think about where is negative 60 degrees, I could add 360 degrees to that and find the positive angle that is equivalent to it, which would be positive what? 300. Or I could find a further one that is negative by subtracting 360 degrees from it. Another negative equivalent would be negative 420 degrees. Now, just the same as that, you can do the same in radians, except you're adding what instead? 2 pi. Now, again, fractions. In order to add 2 pi or subtract 2 pi from pi over 4, what do I have to do? I do have to get a common denominator. What is 2 in terms of fourths? 8 pi over 4, right? I know I put Grant in the sun and he's done. All right, so if I do pi over 4 plus 8 pi over 4, you're here? Still with us? What do I get? 9 pi over 4 would be the forwards one. What would be the backwards one? What's pi over 4 minus 8 pi over 4? Negative 7 pi over 4. All right, and last but not least, number 4. Try that one more time on your own, but this time with thirds. In reference angles, we do see this little alpha sign that I told you earlier. Reference angles are typically always labeled as alpha. So if you ever see find alpha, they're asking you to find the reference angle. Couple main things that you do need to know, though, with this. 1, reference angles are always positive. Okay? So if you ever give me a negative reference angle, you are what? Wrong. Yes. 2, they are always acute. Geometry term, what does that mean? Less than 90. So if you give me an answer that's larger than 90, you are wrong. All right. Last thing, and this is the part that most of us will tend to miss or forget. They are determined by the x-axis and the terminal side. Sometimes we are tempted to use the y-axis and not the x-axis. And I'll show you when that happens. It'll make sense to you in just a second. First off, we're just going to draw them to make sure we know what we're talking about. So if I am given an angle, and my angle is 150 degrees. So let's think about our drawing. We've done this already. Where would 150 degrees fall? What quadrant?
1.
2. Okay? So remember we have like, oh yeah, you need that, remember? 1, 2, the C, 3, 4. Hey, you know what though? That's going to come up a lot if you forget. In your head, you knew where it was. It just wasn't coming out right. All right, so we've got 150s in the second quadrant. And remember we take 90, 180. Which one's it closer to?
180.
180. All right. So if we drew our 150 degree angle, it would look something like this. Yes? Okay, so none of that's different. To find the reference angle, this is where we go back to the key terms. The reference angle is between the terminal side. Remember we talked about we have an initial side. Where's the terminal side? Where it ends. Here, that's what terminal means, the end. Okay, the end of the angle. So between the terminal side and the closest x-axis. Where is the closest x-axis here? This one. This is my reference angle. Okay? So, if my reference angle is this little guy in here, how do I find how many degrees that is? Yeah, that closest x-axis we labeled as what degree? 180, right? If that's 180 and my angle was 150, what's the reference angle? 30. Now, we will not always draw these, okay? For now, we will draw these. Later, we will get used to knowing how to find those or picturing it in our head without drawing it, because eventually it's going to get like too much to just draw everything. So let's try that again with 6. 315. Where is 315?
4.
4. And specifically, where in 4?
In the middle.
In the middle. So I draw, here is my initial side. Here is my terminal side. I do my rotation around. This is my 315-degree angle. Now I think to myself, my reference angle is located between the terminal side. Where's my terminal side?
In the 4th quadrant.
Here. Where's my closest x-axis? Here. I have to find the difference between them. Yes?
Yes, ma'am.
Now, I really don't even have to subtract if I know that this is halfway in between, right? If it's halfway, what's left here? 45, right? So my reference angle, alpha, is this little angle in here, 45 degrees. Now, if you do have to subtract, remember the closest x-axis to 315 would be 360, and you could just subtract. If you subtract those in the wrong order, you will get what kind of number? A negative. Is your answer going to be negative? No, but you could just remove the negative. As long as you remember, it should always be positive. It'll be the same number. Okay? So let's try it with radians. If you're given an angle in radians, you must give me a reference angle in radians. Yes? So, first, again, more practicing with drawing. 4 pi over 3. Where is 4 pi over 3? It's in the 3rd quadrant. And how do I know that? 4/3 is larger than? 1. Yes, because 1 pi is right there. So 4/3 would be a little bit bigger or a little bit more. So right there. Now, that is my 4 pi over 3. So again, reference angle falls between where and where?
The X and the
Terminal side and closest x-axis. Where's that?
Right there.
Here. So what am I subtracting for this one?
130.
I'm doing 4 pi over 3 minus pi.
Pi.
Yes? With the radians, it is more, like you're going to have to think more subtraction. Like that's just how it happens in our heads. 4 pi over 3 minus 1 pi would leave me what? 1 pi over 3. 1/3 pi. Yes. If you need to convert the pi to a common denominator to do that, feel free. Because pi, in terms of thirds, is 3 pi over 3, right? Last but not least for this one, because I don't know if I'm going to give you, I might get you one practice problem before we leave, but pi over 6. Where's pi over 6? It's in the 1st because that's less than a half. 1/6 is less than a half, right? You might not really know where that is. We will after next class. 1/6 is right about there. So, 1/6 pi, if I was to find the reference angle is between what and what again?
The terminal and the X.
Okay, what is that?
That's like Q. It's an angle.
That's pi over 6. I just drew the angle to get that, right? Yeah. So here's a rule for you. If your angle that you're given is in the 1st quadrant, your reference angle is the same as it because the closest x-axis is 0, right? So you're always going to be subtracting 0 if you're in the 1st quadrant. So the reference angle is the same as the original if you're in the 1st quadrant only, okay? Now, one more, and then we will be done. If I gave you the angle theta is equal to, why is that not writing? Theta is equal to 5 pi over 3? No, lies. 7 pi over 6. Theta equals 7 pi over 6. Draw it and find the reference angle.